This is Free Range Digital Design Foundation Modeling. It's Chapter 9 and the first video. We have worked with Boolean functions before, but now we need to add a little bit more terminology with them, some common terminology. And also, we have a couple ways to represent Boolean functions, but now we need a couple more, and these are the most popular ways, and it shows a lot of functionality. And essentially, we're going to develop new ways to represent functions using De Morgan's theorem. So De Morgan's theorem was one of the theorems that we showed a couple slides ago. It was Chapter 6, and we mentioned that there are a lot of theorems there, but we only used a few of them. So De Morgan's theorem, very important. We use it all the time, and it's used in different fields other than just digital design. You see it quite often in computer science as well. We're in the process of representing Boolean functions. There's essentially an infinite number of ways to represent Boolean functions, a few super common approaches, and once again we're going to use De Morgan's theorem to generate some common approaches. This is the function that we developed in Chapter 6. It was a problem. This is the truth table solution. The output is somewhat arbitrary to call. What we did, we said when the output was what we were looking for, we assigned it a 1. So we could have assigned it a 0, and it was kind of what we're going to do in this problem. But what we're going to say here is we're going to write an F bar column. This F bar column is of course in the complement of the F column. So once we do that, we can once again write an equation for 5 ones in this, just like we did before. And in truth, we only know how to write equations for where the ones are. There's ways to write equations directly from the zeros, but we're not going to do that. This problem, we're going to switch to also to A, B, and C just to make it easier to draw. This is going to be F equals, and what I'm going to do is write a term for each of those ones. So I'm going to do it pretty quickly here. And I know there's 5 terms, so I'm going to write 5 product terms. Okay, so those are my 5 product terms, and what I need to do is represent one of these terms for each row where there's a 1. Okay, so the first one is 0, 0, 0. There's 0, 0, 0. The next one is 0, 0, 1. There's 0, 0, 1. My equation is not quite right because it's not F, it's actually F bar. So that's not necessarily what we're looking for. F bar is, could be valid in some cases, but what we want is an equation for F. And so what I'm going to do here is take advantage of one of the other Boolean equations and Boolean theorems here, and I'm going to complement both sides. Now once I complement both sides, because I complement both sides, I'm preserving the equality, and so I haven't lost anything. But what happens here is this F double bar becomes F. Okay, so now I'm at the point where I want to apply De Morgan's theorem, and so it's going to be a couple different approaches. What I need to do is take this overbar down and distribute it between all these terms. So we'll do that. This is going to be, I'm going to do this quick again. There's roughly what I'm looking at, but what I have here is ors changed to ands, and I can write them here if I want. Usually I don't. I'll do it this one time, and then we got this distributed overbar. This big overbar got distributed to these little overbars. These ors here became ands down here. Okay, so I'm still work through this thing. Now this is going to be F equals, but what I'm going to do here is do a De Morgan's theorem on each one of these product terms. Okay, so this is going to take a long time yet again, so I'm going to draw this out really fast. What I have there is an equation with the original overbars in there, but what happens is these overbars need to be distributed between these terms. And notice that the ands associated with these guys became ors down here. So each of these terms and all of these terms needs an overbar coming from that big overbar. We're almost there. This looks pretty messy, but what I want to do is get rid of all the double overbars. Anytime I double overbar something, the overbar goes away. So once again, I'll do this really quickly. So these double overbars, all these are double overbars, so this term is already right. These are two overbars here. This is a single overbar, so I have to retain that one. There's a single overbar. So what I'm doing is just looking for the single overbars. And I found them all, and I am done with this problem. So what I have here is a new special type of equation. Before we had essentially what you'll see in the next slide is the sum of products, but this is product of sums. So these sum terms, you see 5 sum terms there, they're being multiplied together, which is where the product comes from. Now what this is essentially is 2 different representations of the circuit. These representations are functionally equivalent. Now this is a super important word in digital design, you got to remember it. So these 2 equations do the exact same thing, they just do it in different ways. These equations have special names for them. So it's a sum of products, which means these product terms, these are the product terms that are being summed together, sum of products. But because each of those product terms has all three input variables, they become standard product terms, and this equation is officially standard sum of products, which people often write as standard SOP. These terms are these product terms that include all of the input variables are also known as min terms. So this becomes a min term expansion. Each of these are min terms once again because they're product terms, and they include each of the 3 input variables. So as you'd guess, this is a standard sum of products. Which makes it standard is each of these sum terms, standard product of sums. These sum terms are being multiplied together, which is where the product of sums comes from. Each of the sum terms includes all 3 inputs, which makes them standard sum terms. It makes the equation itself a standard product of sums, or standard POS. These are referred to, these standard sum terms are referred to as max terms. So this in the end, this whole equation here is often referred to as a max term. Fancy words, don't see them too often, but you do see them sometimes. This is a chart of min terms and max terms associated with a given example. Okay, so this is actually a 3-bit input. You can see the min terms here, you can see the max terms, but what you want to take away from this is the min term is the complement of the max term is a complement of the min term. So that's what I've written here. Essentially I used this exclamation mark, which I know is the bang character, which is a way of saying I'm complementing that term. Unfortunately, the editor I'm using here didn't have any easy, intelligent way of putting an overbar over it. Oftentimes I will put a bang in front of it in those cases. So for example, the min term, we'll take that first min term there, which is A, B, C. If I complement that, that becomes A plus B plus C. Both of these are double overbarred, which equals A plus B plus C. So this is, once again, this is the max term. The original thing right here was the min term. They are in fact equal to each other. So you could do the same thing by complementing a max term and getting a min term, but we'll go ahead and skip that. Lastly here, these are clunky, to say the least. So what they have here is a way of representing these in what is referred to as compact min-term form and compact max-term form. So the compact min-term form essentially tells me where the ones are. And so and it uses uses the decimal indexes for this. So the compact minterm form is going to be where I see a 1, which is 5, 6, and 7. And so oftentimes what people will write on this is F of A, B, and C, which puts it into proper function format. Sum, as you know, is associated with, the summation character is associated with sums. It makes sense. But we also have a compact max term form, which tells me where the zeros are. And so this is going to, what I'm going to do is look at this F column, see where the zeros are, and write down the decimal indexes, which is 0, 1, 2, 3, 4. And we'll put this in F equals A, B, C, proper functional format. If you look it up in some books here, the pi character is associated with multiplication. I'm not making this up. We won't use it too much, but you oftentimes, or sometimes, you see this written in this compact minterm form. So once again, that's all we have for this set of notes. Once again, we have a bunch of different forms here. We have a standard sum of products, standard product of sums, compact minterm, and compact max term form. They're all different ways to represent a given circuit.